Welcome back. So we've slowly been turning figure 1 and the equations from section 3.1 of the VIT paper into this colorful mess. But it's all organized chaos, and what we're really trying to do is just get our heads around what's going on. Because when you first read a paper, there's a lot happening, but what's our overall goal is we're trying to turn figures or images, math, and text into usable code. So it helps to understand what the connections are between all of this. And so far we've broken down equations 1, 2, and 3. Now we're up to equation 4. And you can see it takes ln, so layer norm, ln. Did you try to figure out what's going on? Now we haven't got the text here, but section 3.1 breaks it down a little bit more. But let's draw a line. We've got the MLP head, and then we've got layer norm. Now, do you recall what MLP stands for? So if we come back here, we'll just set another reminder, come back to equation 4, and just write ourselves a note. MLP equals multi-layer perceptron, and that equals a neural network with X number of layers. So it could have 10 layers, it could have 2 layers. And if you wanted to find out about MLP, what is a MLP? Master Limited Partnership. Oh, we're not going to get that, are we? Do we get? Nope. In machine learning. That's what we want. A multi-layer perceptron is a feed-forward artificial neural network that generates a set of outputs from a set of inputs. Yes, that's what we want to do. We want to map inputs to outputs. So let's come back. What do we got here? Let's read the text. Equation 4, similar to BERT's class token. So this is where reading papers I'm going to jump back around here, but this is on purpose because I'm trying to demonstrate what it's like to read an actual paper rather than just talk about it. So similar to BERT's class token. Now what is BERT? So what is BERT in machine learning? BERT is a type of transformer architecture. There we go. BERT is an open source machine learning framework for natural language processing. So the original transformer architecture was for natural language processing, so processing text. But the vision transformer, recall, turned the transformer, which was originally for one-dimensional sequences of text, and made it possible to use for vision problems, which deal with 2D images. So when the authors reference BERT, they're kind of representing one of the major types of transformer architectures, but originally for text. So the class token is at the start of equation 1, and that's to represent the class that is present. So the class that whatever sample we're trying to classify belongs to. So for the class token, we append a learnable embedding to the sequence of embedded patches. So that's the class token here. So if we go back and continue reading about equation 4, we append a learnable embedding to the sequence of embedded patches. So Z0 equals X class, whose state at the output of the transformer encoder, Z0L, serves as the image representation Y, equation 4. So that's describing equation 4. So if we come back here, equation 4, Z0L, so the 0th token of this output is what we're going to pass to our final layer, layer norm. Well, let's keep reading. Both during pre-training and fine-tuning, a classification head is attached to Z0 of the last layer, L. That's the capital L there, the last layer. The classification head is implemented by an MLP with one hidden layer at pre-training time and by a single layer at fine-tuning time. So if we just want to do training time, we want to go MLP equals one hidden layer at training time or pre-training time, and MLP equals single linear layer at fine-tuning time. So a couple of different interpretations that you can take from that, but let's write it out in pseudocode. So if we look at equation 4, y equals ln of an MLP. Now this is where it also gets a little bit confusing to me. So if we come back to the keynote, it says MLP, but equation 4 doesn't have MLP there. So that confused me a little bit, but I'm pretty sure they mean that this ln is within an MLP. And in fact, if you find that this is different, you can correct me, but I'm going to interpret this ln as being within this MLP head. So let's come back here. In pseudocode, in Python, we want y output because that's going to be the final output. We want y. I'm getting y from here. Y, and this is going to be equation 4, will be an ln layer. So we want a linear layer, so a single hidden layer, wrapping ln layer of x output MLP block. Do you see where that's coming from? X output, so the output of equation 3 is going to feed in to equation 4. There we go there. So that's the linear layer. So an MLP with one hidden layer. We could really do it like this. MLP. MLP, or in our case, we'll just do a linear on the outside. Linear layer. And we can of course customize that to suit our needs. But we have now turned equation 1, 2, 3, and 4 into pseudocode. So what we can now do is start to map this pseudocode to PyTorch code. And so that's what we're going to start doing over subsequent videos, is instead of having this all in pseudocode in the form of math, figures, and text, we want to turn all of this into usable PyTorch layers. So we're going to start working towards doing that. In fact, that's what we've been working towards doing the whole time. But in the next video, I'm just going to break down table 1, and then we'll have all of the pieces of the puzzle ready to start replicating the Vite architecture. If you'd like to jump ahead, you can try to break this table down yourself with reference to the paper. In fact, I'd definitely encourage you to do so. You can find it here, table 1. And then of course, table 1, you can search for different breakdowns. Yeah, model variance, that's what you'll want to read. So give that a shot, and I'll see you in the next video.